Hush, now let's make a small harbor in the dark. I'll speak softly while the room settles, like breath on cool glass. Out there, the new eye in the sky pressed its face to the deep and saw a field sown with thousands of faraway fires, some so old their light began over 13 billion years ago. It lingered where star nurseries sleep behind soft veils and tall, dusty pillars, places where shadows learn to glow. It drifted by a ring with a quiet brim and a wheel threaded with light, wreckage made radiant, then skimmed the pale edge of our own river of stars. Deeper still, a newborn ember flickered, as if the first dawn were still breathing out, hinting that the earliest light may be nearer and stranger than we dreamed. If your heart says yes, a quiet like and a soft subscribe would be lovely. Now let your shoulders drop, close your eyes, we'll begin together, unhurried and warm. For a long time we leaned on glass and metal to ask the dark for stories, and the dark answered in patient crumbs. Then a new mirror unfolded like a golden fern and pressed its face to the deep. What came back was not a single shout, but a hush full of detail, the kind of silence that changes what you believe about how early light learned to breathe. The first scene it shared was a tiny square of sky, small as a grain of sand held at arm's length, tucked in the southern night. In that speck, the view opened like a meadow after snow, thousands upon thousands of distant fires, some carrying light that began more than 13 billion years ago. At the center sat a heavy gathering of galaxies, an ancient crowd whose mass bent the space around it, turning the whole cluster into a gentle magnifying glass. Through that lens, even fainter things in the far back swelled enough to be seen. Thin arcs, soft smears, little commas of glow that would have stayed invisible without the curve of gravity to lift them toward us. This wasn't a lucky snapshot. The telescope settled its near-infrared eye and kept it there, layering exposures at different shades of invisible red, letting the faintest heat dribble in. Hour after hour, about 12.5 in all, the picture deepened, each added sliver of time loosening another stitch in the fabric, until the field looked less like a photograph and more like a memory the universe had been keeping. When NASA released it on the 11th of July 2022, the room went quiet in a particular way, the quiet that arrives when scale suddenly has a face. Infrared was the key. Ordinary light loses its shape on the long road, stretched by the swelling of space, reddened past what our eyes can hold. Dust, too, hides young places, wrapping nurseries and tender spirals in soot, but heat slips through. That is what this mirror was made for, to feel warmth at impossible distance, to listen for embers cooling in the first dawns. For that, it needed to live in shadow. So the observatory sailed to a calm in the Sun-Earth system, a cool porch called L2, about 1.5 million kilometers away, where the Sun, Earth, and Moon all stay to one side, and a silvered shield can keep instruments dim and cold. From there, the mirror rides in step with us, aligned, steady, and quiet enough to hear the softest signals. Look closely at the stars that sparkle in the scene, the ones with sharp, tidy spikes. Those spikes aren't real spears of starlight, not features of the sources themselves. They're the signature of the mirror, a honeycomb of 18 hexagons, each edge teaching the light to diffract in 6 bright directions, with 2 fainter lines from the slim posts that hold the small secondary mirror. It's a kind of halo of the tool, a reminder that every way of seeing leaves a fingerprint on what is seen. In older round mirrors, the mark is a soft ring, an airy blur. Here it is, starlight shaped into delicate snowflakes. Knowing this doesn't spoil the magic. If anything, it makes the view warmer. You can feel the craft in it, the years of careful hands. The cluster that anchors the field had been visited before Hubble knew it. Other observatories knew it, but not like this. Here the background blooms. The arcs look like threads tugged by invisible fingers. Some specks are tiny, barely there, but you can sense their structure: knots, clumps, faint spirals, enough to tell that they are galaxies with histories, not dots. Astronomers sifted that sea and measured how far the light had been stretched. For nearly 200 little beacons they pinned down that redward slide. And for the most distant, it came out around 8 Aleph in the usual scale, a way of saying the light left when the universe was still new, only a few 100 million years into its long morning. What matters in all this, beyond the numbers, is the feeling of time folding. A galaxy is not a blink. It is a habit the universe keeps, a persistence. To see so many of them, so early, is to hear the story of how structure finds itself, how gas learns to settle, how stars gather in spirals and ovals, how collisions bruise and then brighten a shape. The field whispers that the first chapters were busy, not bare. It invites a gentler thought about growth, that order can arise from a long breath, from gravity's patience, from light's quiet labor. The celebration that day was not just for a picture, but for a threshold crossed. The mirror's gold, the careful cold at L2, the folding and unfolding, the tuning of each segment so starlight would meet itself just right, it all worked. And it worked in a way that makes the far past feel near. People who had never seen a spectrum or a redshift still felt the pull, because you don't need the technical words to understand a meadow of lights. You only need to see how much lives in a space the size of a sand grain. The deep field is also a lesson in gentleness. The best way to see something faint is not to stare hard, but to soften and stay. Let the light arrive in its own time. That is what the telescope did. And when the image came together, we could read the fine script, with faint ripples along galactic edges, small whirls, smudges where young stars crowd, dusty lanes where future suns wait their turn. Some galaxies glow warm and smooth, others look ragged, as if still remembering a recent crash. Together they sketch a timeline, how stars were seeded, how metals grew, how the first heavy elements were forged in the hot hearts of massive suns and scattered in their final storms. And then the view shifted southward along our own galaxy's arm to a place not so far as the first deep field, but close enough to feel personal. A grand nebula in Carina, about 8,500 light-years from here. It is immense, larger and brighter than the famous cloud in Orion, and yet quieter in our myths only because most who live in the north have never seen it with their own eyes. In photographs, it looks like weather, cliffs and bays, headlands of dust, valleys carved by light. The telescope's first look into a corner of it, an area called NGC 3324, revealed the cosmic cliffs, a shoreline where newborn stars are pushing back a sea of gas. You can almost feel the wind, radiation and stellar gusts scooping caverns, sculpting columns, drawing lace at the edges where hot and cold meet. Inside this expanse are families of young stars, some gathered in loose clusters that shimmer like frost, others still swaddled. One cluster is astonishingly young, no more than a few 100,000 years old, a blink in cosmic time, its members blue-white and eager, their light and winds already reshaping the neighborhood. Another group nearby hosts giants so bright you can almost hear them. Their lives will be brief and dramatic. This is not a gentle nursery. It is a forge, where the rules are written in heat. At the heart of the region broods a system with a temper known across astronomy, a luminous giant whose outbursts have thrown off great lobes of gas, a star so massive and radiant that it tests the boundary of what gravity can hold together. For a while it was a contender for brightest known in our galaxy. Whether or not it still wears that crown hardly matters. What matters is that it is near enough for us to study in detail, to watch its moods and see how such titans live and shed and possibly prepare for a final transformation. Stars like this are rare, perhaps only a handful in a galaxy like ours at any time, and they feed the future. Their winds enrich the clouds. Their endings seed the next generation with heavy elements. You and I, our bones and blood, owe much to such unruly ancestors. The Carina region shows that star birth rarely happens in a single wave. It comes in pulses, each cluster a stanza in a longer song. Older gatherings sit a little farther out. Younger ones glitter closer to the fresh-cut walls. When you trace the pattern, you can sense time layered like sediment, each ridge and pillar hinting at what carved it. In visible light, some of this is hidden, wrapped in soot. In infrared, the veil thins, and the warm places show themselves. That is the gift here, to see through the smoke without blowing it away, to witness without disturbance. Even the instrument's quirks become part of the story. Those six-pointed stars, the faint horizontal glints, the way an arc curves around a heavy galaxy, each is a clue, a mark of method. The mirror's geometry writes the spikes. The struts add their dimmer echoes. The cluster's mass paints the background with stretched smiles. Once you learn to read these signatures, the field feels like a palimpsest of physics and craft, layered truths resting quietly together. The result of all this looking is not a pile of cold facts, but a softer understanding. A tiny slice of sky holds multitudes. Each sparkle is not a pinprick, but a city of suns, perhaps with planets, perhaps with skies of their own. The more we resolve, the more tenderness seems appropriate, because scale like this can overwhelm, and the right response to overwhelm, especially at night, is to breathe with it. The telescope continues to gaze elsewhere now, gathering new deep fields, unwrapping other nurseries, testing ideas about how quickly the first galaxies formed and how early the universe learned complexity. But that first view remains a touchstone, a proof that patience plus sensitivity can make the far past present. Think of how the deep field and the Carina cliffs answer one another. The first, old city lights from the universe's near beginning. The second, a fresh neighborhood where stars are just choosing their names. Together they sketch a gentle loop, birth from dust, families gathering, shining and shedding, and then new birth from the leavings. If you keep numbers, keep only the kind the heart can carry, is greater than 13 billion years for the faintest glows. The 11th of July, 2022, when that clarity first reached us, about 12.5 hours of quiet looking to lift the invisible to 8,500 light years to that bright cloud in our own arm. The rest is best felt. Arcs written by gravity, mirror-made spikes, a blue-rimmed cliff, a stormy giant pulsing in its shell, pillars cradling small suns. Follow that rhythm, and it leads inward from the far meadow of galaxies to the nearest cradle of light, until the two feel like one breath. Some stars live right on that breath's edge, so restless that each inhale threatens to unspool them. Their light is promise and warning. One day, it will break into something louder than sunrise supernova, even hypernova brief storms bright enough to hush a galaxy. In Carina, such a temperamental heart beats. You can read its voice in the clouds, beside it dark fingers of gas with long, soft tails, all slanting away from the glare, as if a steady wind had pressed a whole sky of tall grass in one direction. The scene we know today is not the scene our great-great-grandparents knew. In the 1,840 seconds, the star flared in what came to be called the Great Eruption, an outpouring so fierce that it climbed to become the second brightest star in the night, outshone only by Sirius, before sinking again behind the dust it had thrown. That blast built a cocoon around the system, a thick envelope that drank the harsh ultraviolet and breathed it back as warmth. In mid-infrared light, that little cloak is the brightest object in the sky, a paradox made simple by dust. What it swallows, it re-emits as a gentler glow. Astronomers, patient with rulers of light, have traced the cocoon's size and tilt with care. They call it the homunculus, little man, as if a small figure had stepped out of the star's own dream, and find it at roughly 7,660 light-years from here, give or take a small margin. Two great lobes billow from the center, each swelling out to about 22,000 astronomical units, like paired soap bubbles joined at the waist. The whole figure leans about 41 degrees from our line of sight, not straight on, not from the side, but at an angle that lets us see its waist and shoulders at once. This is not a quiet fossil. It is still cooling, still changing, still telling us about the violence that made it. Not far away, against a bright background of gas, a small darkness holds its shape like a secret. The keyhole is only a few light years across, about 7 from end to end, but it steals the eye because of contrast, a cold cloud cut in silhouette, its edges lit by fine threads of heated gas that curl and shimmer. In the 19th century, John Herschel wrote of an oval emptiness here, a vacuity with complicated boundaries. Later, a writer named Emma Converse saw what countless readers would also see, the neat shape of a keyhole and the names stuck like dew. Names are the softer kind of gravity. Once a picture has one, it rarely drifts away. The keyhole is not fixed. Photographs across centuries show a face that shifts, filaments brighter, notches deeper, wisps rearranged. The culprit is not motion alone, but weather, radiation and wind from the giants nearby, especially the erratic star in Trumpler 16, whose moods flood the region with energy. Even the confusion of catalogs has a story in it. Some have mistakenly called the keyhole NGC 3324, but that number belongs to a different glow just to the northwest, a young corner where the cosmic cliffs rise. The keyhole itself is its own small country inside the larger Carina nation, a dark room with bright curtains. Within that dark room sits a dense bead of gas and dust, a Bach globule, captured in high detail by Hubble, Carina's defiant finger. Light rakes its edges. The southern tip gleams as if dipped in fire, and you can almost feel it resisting the storm around it. Nearby, massive stars, among them WR25 and a hot blue beacon catalogued in Trumpler 16, bathe the globule in ionizing light. Inside, gravity is trying to fold the gas into embryos of stars. Outside, radiation is hungrily peeling it away. The little clump holds at least 6 solar masses, perhaps cradling newborn suns already. But the ending is written in the conditions. It will evaporate in the glare, not tomorrow, not next century, but soon, in the long telling something like 200,000 to 1,000,000 years. To us, that is forever. To the cloud, it is a single inhale. Carina is full of families. Trumpler 14, compact and brilliant, spans about 6 light-years and sits a little over 8,000 light-years from us. More than 2,000 young stars sparkle there, their combined mass about 4,300 suns. They etch their surroundings with light, burning windows in the dust, chiseling valleys with wind. To the northeast, Trumpler 15 has wandered through a long debate over distance. Gaia's precise measurements set it back into the same neighborhood as its siblings. A confirmation that the whole Carina OB association is truly a clan and not an accident of sightline. Trumpler 16, the elder, larger, more massive gathering, hosts the volatile giant whose outburst made the homunculus. Its radiation does not merely illuminate, it sculpts. The keyhole's profile, the texture of nearby curtains, the slow weather of the region, all of it is a dialogue between source and cloud. Some shapes in Carina have names that sound like fables, and they deserve them. Mystic Mountain, the tall, ridged pillar. Hubble photographed for its 20th anniversary in early February 2010, rises like a storm, stilled mid-gesture. It is about 3 light-years from base to summit, and in its slopes you can trace the work of newborn stars. Jets spear from hidden cradles near the top. Edges fringe and curl where hot winds shear past cold columns. The light of neighboring giants paints the face, revealing cavities, ledges, alcoves where future suns will make their starts. When you look long enough, you forget the scale, then remember it with a small shiver. A single pillar large enough to swallow our entire solar system many times over. And yet, only one thread in a much larger tapestry. Carina is also a catalog of extremes in the language of stars. WR22 is an eclipsing binary, 2 massive suns in a tight dance that makes their shared brightness rise and fall as one passes in front of the other. Estimates vary with method and era as they do for difficult systems, but the primary carries something like 60 to 70 solar masses in many studies, with other work placing it nearer 70 plus. The companion is still a giant by ordinary measures, roughly 20 plus suns. The details shift as models improve, but the picture holds, a pair of heavyweights whose winds and light are stadium loud. WR25. Closer to the heart of the nebula and part of Trumpler 16 is another furnace, one of the more luminous Wolf-Rayet stars in the Milky Way, likely partnered with a hot OB-type companion that hides in the glare. Together they pour energy into the region, a steady, sculpting tide. And then there is HD 93129, a spectacle even by Carina's standards, a triple of O-class beacons. The brighter member, HD 93129A, is itself 2 stars, with the leading one an O2, supergiant, an extreme of heat and mass, its companion a slightly cooler O3, 5 main sequence star. Over the years, careful eyes have watched the pair creep closer in the sky, their separation shrinking by tiny fractions of an arc-second, numbers too fine to feel, but enough to sketch a gravitational bond. A little to the side sits HD 93129b, also O35, almost as luminous as the pair. The 3 together are a kind of lighthouse cluster, their light carving clearings in the cloud. HD 93250. Another fierce lamp, only a few arc minutes from the eruptive giant, complicates simple labels. It is a binary, though the 2 stars refuse to show themselves separately in direct images. Spectrographs and subtle motions betray the pair. Over time, Observers have called its spectral song 05, 06, 5, 04, even 03, evidence of just how hot and bright the components are and how tricky it is to pin them down. In recent work, it has been set as the standard for a newly defined 04 subgiant class, a kind of tuning fork for future studies. When you need to know what an 04 subgiant should sound like, you hold HD 93250 to your ear, and then HD 93205, a tight double wrapped in speed. The larger star sings as an 03, 5 main sequence blaze, so hot that its spectrum carries lines of ionized nitrogen and helium ashes from fusion hauled to the surface by fierce internal mixing. A strong wind roars from it, a river of particles racing into space. Beside it, an 08 companion, smaller but still titanic by human standards, circles at more than 300 kilometers each second. At such velocity, even Einstein's quiet corrections to gravity become audible in the orbit's slow turning, a relativistic precession you can measure if you are patient and precise. To listen to a binary like this is to hear the theory of gravity humming inside a real system, not abstract anymore, but a faint, regular twist in the dance. These bright and volatile lives are short by stellar reckoning. Many will end in spectacular loss, their cores collapsing and their outer layers blasting outward, enriching the surrounding clouds with heavy elements. In a place like Carina, endings are also beginnings. The metals forged in those hot hearts, carbon, oxygen, iron seed, the next generation of stars, and whatever worlds they may grow. It is an old truth, renewed by each image. We are downstream from such fireworks. Far to the north in the sky, in another cloud altogether, a different set of pillars keeps teaching us the same lesson. The Eagle Nebula, about 6,500 to 7,000 light-years away, hosts 3 great columns of gas and dust that Hubble photographed in 1995 under the care of Jeff Hester and Paul Scowen. The picture became an icon, not because it was the first of its kind, but because it captured the feeling of a nursery at work. Finger-like towers, several light-years long, textured with shadow and glow, their tips freckled with little knots. Those knots have a gentle name, evaporating gaseous globules, EGGs, and inside them, gravity is gathering material the way a slow hand gathers thread. When the cores are dense and hot enough, fusion lights, and a young star begins to push back the very cradle that sheltered it, jets slants out, cocoons thin. Bright rims appear where radiation gnaws at the edges. Creation here comes paired with erosion, a tenderness, and a devouring in the same breath. Long before the famous color frames, the pillars were only hints on glass. In 1920, John Charles Duncan noted dark trunks on a photographic plate from the 60-inch telescope at Mount Wilson, captured in the era when our picture of the galaxy itself was still forming. Decades of better mirrors and cameras later, the towers stepped forward with a clarity that let anyone, expert or not, read the story. Scale helps. The leftmost pillar is about 4 light-years in length, 20+ trillion miles, and each column could swallow our planetary system many times. But you don't need numbers to feel why the scene matters. The pillars are beautiful, yes, but they are also temporary. The same newborn stars that the trunks cradle are eating them from within and without. One day the towers will be lace. One day the lace will be smoke. One day even the smoke will be gone, and the region will glitter with the suns the pillars helped raise. Back in Carina, the rhythm is similar, only louder. Giants pour light. Dust sculpts itself into walls and caves. Globules incubate and then evaporate. Clusters light the ceiling. The great eruptions twin, bubbles cool and fade. The keyhole changes its profile. Mystic Mountain grows ragged at the edges as new jets and shocks rework it. Through all of it, the telescope's way of seeing matters. Invisible light, soot hides the nurseries. In infrared, the veil thins and the warm hearts shine through. You get a sense of time layered on time, older clusters farther out, younger ones nested closer to the cutting edge, where pressure pushes into the cloud. Star formation happens in waves, like surf coming ashore. And always, the edge of catastrophe haunts the brightest lives. A star 100 times the sun's mass glows millions of times more luminous. Its outward pressure batters its own gravity, and the balance never feels entirely safe. Some cross limits, some eject shells, some endure in uneasy truce until the last fuel goes. When the end comes, it is fast and luminous. For a week or a month, the ruin shines harder than a whole galaxy, then declines into a nebula, a remnant, a rearranged neighborhood. We watch not to mourn, but to understand the trade. Fierce light for short years, quiet, long ages for dimmer stars like ours. The numbers we keep are small enough to carry in one hand. The distance to the homunculus, about 7,660 light-years, with a modest uncertainty that reminds us even our best measures breathe. The reach of its lobes around 22,000 AU. The tilt about 41 degrees. The keyholes span roughly 7 light-years. Trumpler 14's size, about 6 light-years, and its population, some 2,000 young suns, with a shared mass near 4,300 solar. The Eagle Pillar's lengths 3 to 4 light-years. The Eagle's distance, something like 6,500 to 7,000 light-years. A few masses and velocities, companions at 20 suns, primaries at 40 to 60 or more. An orbital speed above 300 kilometers per second that lets relativity whisper. These are enough to anchor the pictures without weighing them down. Now, let the images carry us the rest of the way. Dust carving its own galleries, a jet drawing a straight stroke through a bending cloud, a cluster's light kindling a rim, an old eruption leaving a dumbbell of cool gas adrift in the dark. You don't need to memorize the catalog to feel the truth of it. The universe builds with breath and brightness, and even its violence keeps a kind of order, cycles repeating, structures rising and dissolving, seeds carried forward from one generation to the next. If you listen closely, there's gentleness under the drama, radiation, fierce, yet also a steady touch that shapes, winds, harsh yet patient sculptors that cut canyons, polish pillars, teach edges to glow. Even our naming misplaced NGCs, poet-born nicknames, becomes a tenderness, an attempt to hold things long enough to learn from them. And while the brightest stars test their limits, our instruments test ours. Mirrors aligned so finely that starlight meets itself at a perfect point. Cameras keeping still in deep cold, listening for whispers. Spectrographs splitting light into songs. We can read lines and bands telling of temperature, speed, composition, wind. When a number won't fit a model, a mass a little low for the given heat and shine, that mismatch is an invitation, not a failure. We refine, we watch longer, we let the sky teach what our equations missed. And when the lesson turns to color, we remember that even color can be a lullaby rather than a literal map. That famous scene wears such a lullaby. Those hues aren't what you'd see drifting there in person. Hubble stitched them from 32 careful looks through different filters, each tuned to a single voice in the gas: hydrogen singing green, sulfur humming red, oxygen whispering blue. Layered together, the notes become those surreal blues and embers that made 3 cold columns into a living painting. Along the bright edges, you can read where nearby ultraviolet light is licking the gas, heating it, charging it, making rims glow like frost at sunrise. And the little step missing in the upper right corner? Not a wound, just the camera's signature. One quadrant of WFPC, too magnified more than the others. When astronomers scaled the views to match, a tiny gap remained, a staircase tucked inside the frame. Many Hubble portraits carry that small flourish, shifting with how the image is turned to meet the world. After 1995, the picture walked out of the journals and into daily life. It found its way to classroom walls, magazine covers, mugs, and t-shirts. It became a shorthand for wonder. The phrase that named it Pillars of Creation was borrowed from an 1857 sermon by Charles Spurgeon, a religious image repurposed to christen a stellar nursery. The words stuck because they felt true to the site: towers where stars are made, beauty paired with patient work. The region did not stop speaking after that first portrait. Different observatories returned with new ears. In 2001, the Chandra X-ray Observatory glanced across the same patch. It did not find strong X-ray beacons buried deep inside the columns, no crowd of massive newborns blazing yet from within, but it did catch X-rays from young stars scattered nearby, a quiet confirmation that the neighborhood was busy. Chandra's processed data, released to the public in 2007, added another layer to the story, where the hottest, most energetic activity leaves its faint, hard glow. By 2010, the European Space Agency's Herschel Observatory looked in far infrared, the kind of light that slides through dust. It peered into the columns' bellies and saw the cold cores where stars are gestating. In those views, the towers are not just silhouettes, but cradles with beating hearts, their densest knots wrapped in blankets only infrared can see through. Those measurements helped show how the same ultraviolet light that gives the pillars a luminous edge is also carving them away, eating into the clay even as it helps shape it. A silver anniversary brought a sharper gaze. In January 2015, to mark 25 years in orbit, Hubble returned with its newer wide-field camera, 3 installed during a 2009 shuttle mission, and released a larger, crisper version of the scene. The base of the pillars resolved into finer textures. Faint stars that had been hidden stepped into view. An infrared companion image arrived alongside the visible one, letting everyone see through the dust and meet the infants still tucked inside. The two pictures together felt like before and after, and inside and outside, all at once. Surfaces burnished by light, interiors bright with beginnings. Between those celebrations, Spitzer, another infrared eye, noticed a warm, oddly shaped cloud near the pillars. Its heat and outline led some scientists to suggest a dramatic backstory. Perhaps a supernova's shock had already swept through the region around 6,000 years ago, unspooling the towers, with the ruins' light still in transit to us. Because the Eagle Nebula sits roughly 6,500 to 7,000 light-years away, we would be watching a ghost that will not admit its own ending for another 1,000 years. Others urged caution. If a nearby supernova had detonated, stronger radio and X-ray signals should linger. An alternative fit the data more gently. Fierce winds from massive stars could heat dust into the same shape without a single explosion. Under that reading, the pillars are not gone. They are simply steadily eroding under relentless radiation and ongoing weathering that will, in time, unmake them. As instruments improved, revisits kept their promise. In October 2022, the James Webb Space Telescope turned its near-infrared camera toward the familiar towers and showed them new. Tiny red glows freckled the edges, young stars in early phases, still wrapped in the material that made them. Filaments and wisps resolved into exquisite strands, curls, and shock fronts, as if the columns had grown finer grain. The feeling was the same and deeper, a nursery humming under its own breath. Then, in June 2024, NASA released a fresh visualization, a 3D rendering built from Hubble and Webb data, a multi-wavelength flight that lets you drift around and through the pillars. It is the most layered movie yet for this place. Visible light for bright skins, infrared for hidden rooms, so you can feel how stars sculpt their house as they grow. Behind the color and cameras is a simple, tender physics. The pillars live in the Eagle Nebula, part of the Carina-Sagittarius arm of our Milky Way. Bright, young, massive stars ionize the surrounding gas. The gas glows softly in their light. Where dust runs thick, it blocks the glow and carves the dramatic silhouettes. Within those silhouettes lie clumps, dense seeds called EGGs, at the fingered tips that act like little shields. Each one, many times larger than our solar system, absorbs most of the ultraviolet that would otherwise strip it bare, casting long shadows that protect the material behind. Safe in that shade, gravity gathers matter until the core densifies and heats. Fusion catches. A star is born. The cocoon thins, the infant brightens, and jets fire from the poles, scribbling straight lines into curving cloud. In time, the EGG evaporates, revealing a new sun where a knob of darkness once perched. This is photoevaporation sculpture. Light breaking molecules apart, warming the gas, lifting it away. Over tens or hundreds of thousands of years, the towers soften into lace, then into mist, then into memory, while the stars they made go on shining. The material is simple as well, mostly cool molecular hydrogen with dust and traces of carbon, oxygen, sulfur. In the densest knots, temperatures hover only a few tens of degrees above absolute zero. Cold doesn't mean still, though. Pressure, gravity, and radiation play their long game. The same ultraviolet that gnaws the surface also compresses some pockets, speeding collapse. The balance between pushing and pulling paints the shapes we know. Watching those shapes across years, astronomers can measure how fast gas is being lost, how often cores ignite, how quickly jets carve cavities. It's a way to rewind our own history. The sun and its planets likely formed in places not so different from these, inside a dusty nursery whose towers have long since fallen. No single wavelength tells the whole truth. Visible light gives us the bright skins, the gores and hems where radiation meets shadow. Infrared peels back the soot and shows the interiors, the embryos, the newborns. X-rays pick out the hot, violent edges, the outflows, the flares. Together they speak in chorus about a cycle that never pauses, cooling and heating, hiding and revealing. The slow trade between destruction and birth. That is why the pictures feel both calming and alive. They show change at a pace we can barely sense, but our bodies recognize the rhythm. Inhale, exhale, gather, release. The tools themselves have biographies worth a quiet nod. WFPC-2, the camera that made the 1000, 995 portrait was a 4-chip workhorse that turned mirror-collected light into digital frames and taught the public what space could look like. In 2009, astronauts cradled a new instrument, Wide Field Camera 3, into Hubble's belly and brought WFPC-2 home. You can stand in a museum now and face the machine that gave us one of the century's most beloved images. Spitzer, cooled and listening in, infrared, added warmth to the story before retiring. Chandra continues to hear X-ray whispers. Webb hums at L2, cold and sharp, extending the tail into finer threads. None cancels the others. Each sees what the others cannot, and together they let us walk around a truth the way you might walk around a sculpture in a dim gallery, noticing different lines each time. If you tilt your attention outward from nurseries to collisions, another marvel waits, a wheel of light in a darker field. The Cartwheel Galaxy lives about 500 million light-years away in Sculptor, a ringed system born of an ancient impact. It is lenticular in one sense, smooth disk, subdued bulge, and yet it wears a bright, expanding ring where stars, gas, and dust have been swept into a circular wave. Its measured diameter at a standard brightness reaches roughly 188,000 light-years. Its outer ring turns with a speed near 217 kilometers each second. Numbers like these are waypoints, not destinations. They tell you the ring is vast and in motion. They hint at a blow long ago, a smaller galaxy plunging through a larger disk and sending ripples racing outward like a stone thrown into a pond. At the rim where the wave passes, gas compresses, stars ignite, the circle becomes a string of fire. All these scenes, the columns, the eggs, the wheel, carry a softness beneath their drama. The universe is not only explosions and equations, it is patient weather, light washing edges, wind combing dust, gravity laying down curves that later eyes can trace. Color is a translation true to the physics, yet tuned for human sight so we can learn without hard squinting. Dates: 1995, 2001, 2010, 2015, 2022, 2024 feel like stones along a footpath, each marking a breath held by a new instrument that saw a little more. And distances 6,500, 7,000 light-years to the Eagle, 500 million to the Cartwheel, speak less of remoteness than of time. We are always looking into the past, and the past is always arriving. A gentle tide of photons bringing us news. Follow that tide, and one image steps forward from the hush. A wheel, faint at first, then unmistakable. The wheel in the dark was first found on old glass, a circle whispered into being by starlight and patience. In 1941, Fritz Zwicky paused over deep plates and felt the tug of something unusually arranged. A ring, a hub, hints of spokes. He called it among the most complicated stellar systems, waiting for an explanation in gravity's language. Zwicky was a stubborn dreamer, early to imagine unseen matter binding galaxies from the shadows, unafraid to say what the data only half admitted. Time proved him right more than once. Here, too, the wheel would teach that a single passage through a disk can ring a galaxy like a bell, and that the sound lingers as light. Measurements sharpened with decades. Under the cool rigor of catalogs, the circle gained numbers to steady the awe. A D25 diameter, near 60.9 arcseconds, which, At a distance of roughly 132 million parsecs, about 431 million light-years, becomes to 57.7 kiloparsecs, around 188,200 light-years across. Slightly larger than Andromeda, already a giant in our local reckoning. You don't need the arithmetic to feel its scale. The arithmetic is there to comfort the part of you that counts when it is overwhelmed. The rest you can hold as a shape, a bright ring, a dimmer heart, a lace of dust, like smoke between. It does not drift alone. The wheel sits at the center of a small family, 3 neighbors looping or drifting nearby under a shared pull. Astronomers tag them G1, G2, G3, a clean set of labels for a messy dance. G1 wears the look of a blue, irregular spiral, like the smaller companions that flank our Milky Way. G2 is a compact yellow spiral with a thin tidal tail, a ribbon of stars and gas tugged out by past stress. G3 lies farther out in most wide-field frames, a more distant spiral to the eye. Together they make a neighborhood with short tempers and long memories, where gravity plays rough and beauty falls out of the scrapes as often as scars do. Only one supernova has announced itself in the wheel so far, a Type 2, caught in late November 2021 by vigilant survey eyes. It was faint by the time we met it from 500 million light-years away, a magnitude around 18.8, barely a prickle unless your mirror is large and your skies are gentle. Still, the note matters. It says that in the outer ring, where stars have been flaring into life at a furious pace, some have already run through their brief fuel, collapsed their cores, and sent shock into the dark. The ring is young in cosmic terms. The deaths have begun anyway. Look at the structure as if it were something you could touch. The bright outer rim is where the action lives. A wave front of compression, pushing through gas and dust, igniting star formation as it goes. Inside it, a softer, smaller ring circles the nucleus, and between the two runs a dark band, a nuclear dust ring that drinks starlight and reveals itself by what it withholds. Faint bridges and bars connect inner and outer like spokes, but their identities change with the light you use to see them. In radio, some spokes are non-thermal, born of electrons spiraling in magnetic fields, a whisper of cosmic rays. In optical light, others show up as delicate chains of stars and dust. The mismatch tells a simple truth. Different processes paint similar shapes, and one view is never the whole. The story that best fits the evidence is an elegant accident. A few 100 million years ago, 2 to 3, give or take, something smaller, plunged straight through the disk of a normal spiral, a bullseye strike. Not a grazing pass, not a slow tidal tease, a direct transit through the living plane. Gravity jumped at the chance and sent a circular ripple outward through the disk, a density wave like a ring from a pebble in a pond. Where the wave moved, gas squeezed. Where gas squeezed, stars turned on. The outer ring looks blue because its massive newborns are bright and short-lived, pouring hard light before fading to embers. The inner parts, away from the shock, stayed calmer, holding to older, warmer tones. If you could run the clock with your hands, you would watch the bright circle widen, dimming as it spends itself, while the central regions start to sketch new arms, faint spirals reaching outward. The first hints of a galaxy, regathering its more usual form. Not every theorist was satisfied with a single cause. Another idea, quieter and more internal, suggests the disk itself can grow patterns when gravity and rotation nudge it past certain thresholds. Genes instabilities That's seed rings and spokes without a collision at all. It is a useful lens to try on many disks, and in some, it may be enough. But the wheel's specifics, its rings' youth and brightness, the way the spokes behave across wavelengths, the disturbed companions fit the impact story better. When the community holds both pictures against the sky, the bullseye wins on points. Deep radio maps add a decisive thread. Neutral hydrogen, H1, the simplest atom in its quiet state, draws long, faint lines across space and bears gossip about past encounters. In the wheel's neighborhood, a tale of H1 links the system to G3, the more distant companion in visible frames. That bridge says G3 is not merely sharing the view but the history. It is bound in motion and likely the true bullet that passed through. The age of the ring, on the order of 300 million years, matches the time such a shock would need to sweep outward to its current radius. G1 and G2 sit closer now, but their positions do not line up with the path a collider would have taken, while G3's greater remove about 88 kiloparsecs, 287,000 light-years, from the wheel's center. Makes sense for an object that has already crossed and continued on. In other systems, you can see gas tails trail behind galaxies, like scarves pulled by the wind of a cluster's hot medium, a process called ram pressure stripping. Here, though, much of the gas forms leading structures, bridges ahead in the direction of motion, a signature more faithful to the violence of a direct collision than to slow weathering by environment. Nothing about the wheel is static. The outer ring stars pour their light into the dust and gas around them, ionize the nearby hydrogen, and beat on the medium with winds. They carve nebulae along the rim, blow superbubbles, and leave little pockets where the next generation is already stirring. As the wave drifts outward and weakens, the ring will lose definition. Material that rode it will lag, slow, and begin to fall inward, feeding bars or fresh spiral arms. Given a few more 100 million years without another blow, the disk may smooth into something closer to a classic spiral again, its wild wheel moment recorded only in the distribution of ages along its radius. Or, if the companions stray too near, the wheel may be rung again, delayed in its settling, reshaped by a second impact. Group life makes firm predictions soft. What makes the wheel so instructive is not only the shape, but the conditions the shape creates. A ring-driven starburst is a laboratory under pressure. Gas is compressed hard and fast, turbulence is strong, and clusters are born in batches. Many of the clusters carry massive members that blaze blue and die young. Some end their brief lives as core collapse supernovae that leave neutron stars or black holes. In a place like the wheel's rim, those remnants often find partners. If a compact object orbits a normal star, it can sip or gulp from the companion's wind or surface. The infalling gas heats as it spirals in, flaring bright in X-rays. When X-ray telescopes look along the ring, they find a rash of such sources, ultraluminous, even hyperluminous in some cases, white points concentrated along the circumference, like dew. The brightest are probably black holes feeding. The quieter ones may be neutron stars with strong fields. Each is a diary, where a massive star's life ends and a high-energy story begins. Spectra add their own music. In the outer ring, the light carries strong emission from ionized hydrogen and oxygen H2 regions, lit by the harsh glow of young O and B-type stars. Infrared frames show dust warmed by that same radiation, shining as it re-emits the energy in longer waves. Radio lines and continuum paint both thermal breath from UC2 clouds and non-thermal synchrotron from cosmic rays, accelerated in shocks, and supernova leftovers. Lay the wavelengths together, and you see a system in transition, not one that has been wounded and left to drift, but one building vigorously in the same places where it was broken. The wheel's companions bear marks of the same drama. Arms are stretched, discs kinked, outer regions ragged where tides have pulled and flexed them. If you watch pairs and small groups long enough in simulations, you learn the choreography. Close passages, stir bars, launch arms, induce inflows, gas piles up and forms stars. Then the pieces swing apart and return, their orbits decaying a little if dynamical friction has its way. Given enough time, and unless new energy is pumped in, small groups tend to merge to fewer, larger bodies, ellipticals or lenticulars, that remember their past only in shells and kinematics. The wheel's group may follow such a path across a few billion years, or it may meet other neighbors and write a different ending. The specifics matter to the models. To the mood of the night, the lesson is simpler. Galaxies are social, and their lives are altered by their company. To test ideas like this, astronomers build universes in silicon. Feed a code the mass and shape of a disk, give it a bullet galaxy with a certain trajectory and speed, and watch what happens when one passes through the other. In run after run, the same pattern rises. Circular waves march outward, compressing gas that then lights in a ring. Spokes appear where bars, ripples, and magnetic fields guide material between rim and core. The synthetic images look like the real ones, which is always a consolation. The math turns into pictures that match the sky. The wheel, in turn, gives the codes a foil to struggle against and refine. Mismatches in detail become clues to missing physics. Part of the public love for this galaxy is easy to explain. It really does look like a wheel, a luminous hoop of blue young things around a darker hub, with dusty lanes like the pattern left on a road by something that rolled through. Hubble's crisp sight showed the spokes. Webb's deeper infrared pulled out the fainter filaments and the youngest clusters hiding in cocoons. Color made the map legible. Cooler, older light warming the core. Hot, newborn light making the rim. Electric, dust weaving shadows between. To sit with such an image is to feel design where there is only consequence, our minds being what they are, and then to let that sense of design soften into a more generous awe. Gravity and time can draw beauty out of accidents. Collisions like this are not rare. The universe is big, but it is not empty, and orbits cross. Our own Milky Way moves toward Andromeda right now on a long, slow collision course with a first close pass in about 4 billion years. The meeting will not be a crash in the everyday meaning. Stars are too far apart for that, but it will be a profound rearrangement. Disks will buckle, tails will grow, rings and shells may form, black holes will be fed. If you need a preview that is both strange and strangely familiar, the wheel offers it from 500 million light years away. A ring like a ripple, a brightening like a bruise, a path back to calm afterward, if no new trouble intervenes. All of this has been traveling to us for a long time. The light that curls across your retina or a camera's pixels left the wheel before hands learned to press stories into clay. What we're shown is an after ring, the widening circle, the roused companions, the bright rim seeded with newborn suns, and the first small cemeteries of their dead. On the scale of the cosmos, it is recent. On the scale of a life, immovably far. That mismatch can feel cold, and yet it's tender too. We are small, and still we fashioned eyes that read such distant weather. If you want anchors to take with you, and let the rest stay as texture, a diameter near 188,000 light-years, a distance around 431 million light-years, a ring 200 to 300 million years into its expansion, a likely bullet G3 tethered by a bridge of neutral hydrogen, one recorded supernova in 2021, quiet but sure. Spokes whose radio and optical versions miss each other by a beat, an outer rim alive with blue light, and pinprick X-rays, the marks of birth and aftermath, together. Touch them with the mind's fingertip, set them down again. What remains is a feeling, a galaxy wrung like crystal, singing in light, neighbors holding the same refrain, gas becoming stars, in a bright circle that will one day thin and blur, a core biding its time to grow arms again, dust riding, erasing, riding anew. Somewhere inside that wheel, a modest cluster is beginning a long, quiet span. Somewhere else, a giant is ending in sudden brightness. Between them, winds ferry elements toward worlds no one will ever see. It's enough to let the image float and the explanation settle softly behind it, where the universe colliding and composing in the same motion, while the wheel turns quietly in the dark. And then, easing our gaze from the ringing circle to a smaller register of blue, something compact keeps its own time. In the quiet fields beyond our familiar patterns, a tiny ember burns with a stormy signature. IZU 18, a blue compact dwarf, rare enough to wear the mark of a Wolf-Rayet galaxy, where some stars are so hot and massive, their winds peel the night like weather. It lives in Ursa Major, about 18.44 megaparsecs, near 60 million light-years, small to the eye, startlingly young-looking, wrapped in faint gas, where new suns are learning their names. It first brushed human sight on deep photographic plates in the 1,930 seconds, when Fritz Zwicky, sharp-eyed and stubborn in his curiosity, marked it down. He could not have guessed how often this little system would be asked to explain the early universe to us. Decades later, as Palomar and other ground observatories leaned in, the galaxy kept delivering puzzles. Its center gleamed with unusual energy, for so small a thing, an active heart by some measures, as if a compact engine, a clutch of massive stars, or perhaps a small black hole, were stirring the core. But the larger surprise was its face, so blue, so bare of heavy elements, so much like the distant newborn galaxies seen near the edge of time. When Hubble spread its golden net in orbit and turned toward IZU 18, the first look seemed to confirm an audacious idea. Early images gave the impression of a galaxy no older than to 500 million years, a blink in a cosmos filled with ancients. If true, it would mean this dwarf delayed its becoming for almost the whole age of the universe, only now kindling into starbirth, while its neighbors had long since grown up. The thought bent our models. In the usual telling, galaxies like this finished their first busy chapter billions of years ago. A latecomer so near felt like a misprint in nature's book. The misprint, it turned out, was ours. As Hubble's instruments grew more sensitive, astronomers picked out fainter, redder specks hidden among the vivid blue. Old stars, hard to see at first, emerged quiet witnesses at least 1 billion years of age, perhaps as old as 10. IZU 18 wasn't freshly minted, it had history. What made it look so young was a long, slow life with very little star-making, followed by a sudden burst that lit its compact body like a flare. Spectra told the same story in another language, hydrogen and helium everywhere, with only whispers of heavier elements, metal poor, almost primordial, not because time had forgotten it, but because it had not been busy enough to enrich itself until recently. That chemistry drew a crowd. Spitzer sifted its infrared warmth, the dust, the pockets of gently heated gas. Chandra looked for hard, high-energy whispers, hot clouds, possible remnants of old supernovae, knots where newborn giants had already died. The far, ultraviolet spectroscopic explorer traced the young, blistering stars at the bright core. And then Webb, colder and keener, began to peel back more layers, catching faint light that Hubble could not untangle. The question kept pulsing beneath the data. Why so quiet for so long? And why this sudden fire? In 2015, another clue lit up. Astronomers mapped an unusually large swath of ionized helium, He-2, inside the galaxy, a signature more familiar in very distant, very metal-poor systems from the universe's first mornings. It takes fierce photons to strip electrons from helium. Ordinary hot stars struggle to do it at the scale seen here. The findings stirred a daring thought. Perhaps Izov 18 shelters a few stellar furnaces that behave like the universe's first generation, population 3, or at least their close cousins. Those original stars would have been forged from pure hydrogen and helium, lived fast, and vanished early. To find their echoes now, in our galactic neighborhood, would be like hearing a lullaby from someone long gone. Nothing yet proves that such primordial giants burn here today, but the helium glow, the extreme scarcity of metals, and the intensity of recent starbirth keep the door open a crack. Measuring the galaxy's distance precisely sharpened the picture. A team at the Space Telescope Science Institute, together with ESA, searched IZU-18 for Cepheid variables, stars that breathe in and out with a rhythm that betrays their true brightness. 3 were found, their pulses timed and compared to models tuned for low metallicity homes like this one. The result, about 59 million light-years, was farther than early guesses. That extra stretch explains why Hubble at first missed the oldest, faintest stars. They were right at the edge of what even a great eye could resolve. With distance fixed, size and shape snapped into better focus too. What the galaxy lacks in width, it makes up for in intensity. Against the Milky Way's to 100,000 light-year span, IZU-18 is tiny, about 1.58 kiloparsecs, roughly 5,150 light-years, across an island lit, mostly by 2 compact, feverish, star-forming knots near its center. Through Hubble, the core shines bluish-white, studded with clusters that sparkle like chips of ice in sun. From those knots, faint filaments drift outward, gas, driven by stellar winds and past supernovae, layered shells that trace the breath of successive generations. Ultraviolet light from the newest stars washes the bubbles, making them glow. Shock waves compress nearby clouds and set the next round of stars to forming. The history isn't written as a straight line, but as rings and ripples overlapping bursts, each sculpting the stage for the next. By taxonomies we use to keep our thoughts tidy, the little galaxy wears many labels: dwarf, irregular. It will not sit still for a neat spiral or an oval. Blue, compact. Most of the light comes from hot, young stars crowded into the heart. Starburst. For now, it is spending fuel quickly, turning gas into suns at a rate that rivals much larger systems. Wolf-Rayet. Among its firebrands are stars so massive and evolved that their winds roar, their emission lines bright with helium, carbon, nitrogen. Each tag is a window, not a box. Together they say, small, metal poor, suddenly busy. The chemistry keeps telling its quiet truth. In places like our galaxy, the interstellar medium has been seasoned by many cycles of star life. Carbon, oxygen, sulfur, and heavier elements salt the gas. In IZ-18, those metals are scarce. Temperatures in the densest pockets sit just tens of degrees above absolute zero. Still, gravity finds a way. Cores collapse, fusion lights, and with each new crop of stars, the galaxy adds a little more metal to itself. It is a living lesson in how the universe grew complex from simple beginnings, hydrogen to helium, to the first seeds of everything else, step by slow step. Seen up close in mind's eye, the core is a busy nest. Two dominant nurseries blaze, each a tangle of dense gas veils and infant clusters. Around them, thin blue mist marks outflows, winds, and past blasts painting faint arcs. Some of the brightest members will die young, their ends writing small X's in Chandra's charts. Others will spin down into ordinary middle age, lighting the galaxy more gently for long spans. Between them, compressed ridges will ignite, and the starburst will walk across the center in little leaps, each new wave echoing the last. To know how old a place like this is, you need more than color. You need a clock. Cepheids gave that, and with the distance clarified, earlier contradictions softened. The older red giants that Hubble struggled to cleanly separate at first, so dim at this range, became visible enough to prove their case. IZ-18 is not a cosmic teenager. It only dresses like one. That dressing, though, is not cosmetic. The lack of metals means fewer cooling pathways in the gas, changing how clouds collapse and how stars form. The bursty history suggests that for most of its life, the galaxy either lacked the triggering nudge, or lost gas to outflows, or simply drifted in a quiet lane until something, perhaps a passing cloud or dark matter substructure, jolted it into activity. The instruments keep teaching, each at its pitch, Spitzer's infrared mapped dust that our eyes cannot see, showing where starlight has been absorbed and re-emitted as warmth. Chandra's X-rays picked out hot gas and compact leftovers, places where massive stars ended and left their signatures. Fuse listened to the far ultraviolet, a direct voice from the hottest, youngest stars. Webb's near and mid-infrared vision peeks through even thicker veils, pulling older, redder populations into view and tracing tiny structures in the core that Hubble could not isolate. Layered together, the images make a kind of 3D lullaby. Cold shells, warm dust, hot knots, all moving on different clocks, all telling one story. If you stand back, the shape is simple enough. A ragged little island, two bright hubs, faint tendrils, a halo of gas that has not yet found the courage to fall in. Its diameter, about 5,150 light-years, would tuck inside the Milky Way's central bulge. And yet, in that small room, the star formation rate at present rivals galaxies 10 times bigger. Blue light gushes from short-lived giants. Emission lines carve the spectrum. Winds rattle the gas into scalloped edges. You can almost see the future. Today's pressure becomes tomorrow's nursery. Today's supernova seeds tomorrow's chemistry. The process that made us hydrogen into heavier things runs here in miniature, like a tabletop forge. The helium-2 glow remains a soft whisper from the past. There are other ways to make it: X-ray binaries, fast-rotating massive stars, shocks, but the romantic possibility persists that somewhere in the blue thicket, a few stars are nearly as metal-free as anything in our time can be, hot enough to push helium over the edge. If they exist, their lives will be brief. They will leave little behind but patterns in the light and metals in the gas. The clue is fragile, but in a place so poor in heavy elements, it feels honest to entertain. Even the galaxy's chaos has a kind of order. Dwarf irregulars often look scattered because small systems are easy to stir by winds, by outflows, by tides from passing masses we cannot see. In the center, however, IZU 18 is organized by urgency. Two bright knots dominate. Around them, shells and filaments outline the pressure waves. Farther out, faint, ragged arcs mark where gas has been blown and is cooling. In deep Hubble frames, the background is a tapestry of far-off galaxies, each a smudge, all older and larger, reminding you that this little blue island is not alone but embedded in a sea. The distance measurement that settled near 5960 million light-years did more than calibrate a scale. It clarified why the old stars hid, why early looks were fooled, why models bent until better data arrived. It also sharpened estimates of size and brightness, message and meaning. The galaxy is small, yes, and violently blue now, but it is not newborn. It has been coasting a long time, then sprinting. That rhythm long rests. Short runs may be common in low-mass, metal-poor dwarfs, especially those living in relatively quiet neighborhoods where nothing big shakes them until chance or drift delivers new gas. What comes next hides in the same questions that brought us here. Will the current burst burn through the available fuel and return the galaxy to quiescence? Will fresh gas, from filaments or faint companions, fall in and restart the fire? Will Webb find even older, fainter stars tucked deeper than Hubble could reach, pushing the galaxy's first chapter further back? Little systems like this are exquisitely sensitive to small changes. A handful of supernovae can drive outflows that alter the next 100 million years. A modest inflow can repaint the core. For now, the facts that matter fit in a palm. A distance near 60 million light-years, a body only to 1.58 kiloparsecs wide, metallicity so low it feels like dawn. Two brilliant nurseries sparking near the center, faint, layered shells from winds and past blasts. Older stars, at least 1 billion years old, hiding under the blue. Helium-2 that hints at extreme engines. Cepheids ticking, 3 steady pulses that fixed the scale. Around those beads, you can string the feeling. A time capsule still running, a living echo of the universe's first work. And if you let the numbers soften, what remains is simple and kind. In a small, bright knot of stars, hydrogen and helium are being coaxed into heavier things. Dust is learning to glow. Gas is being carved into rooms where the next generation will lie down. A galaxy that looked young only because we could not see its elders is teaching us the patience of better eyes. Somewhere inside that blue fire, a cluster is forming that will live longer than we will. Somewhere else, a giant is already ending, and its ashes will become the marrow of future suns. The early universe is not gone. In places like IZU 18, it is still audible, still breathing, still offering us a gentle way to remember how simple things became complex and how light found its voice. Dark wreaths circle a sideways world, 13 in all, each a thin whisper of matter pinned to an equator that lies almost in its own night. They're more intricate than the skimpy lanes at Jupiter or Neptune, yet shy beside Saturn's bright, broad avenues, neither simple nor grand, but intimate, precise, and strange. The modern telling begins in a hush, the 10th of March, 1977. One steady star in the background, Uranus sliding in front. 3 astronomers aboard the Kuiper Airborne Observatory, James Elliott, Edward Dunham, Jessica Mink, were watching for the planet's atmosphere to dim the starlight. Instead, the star blinked 5 times before the planet arrived, then 5 times after. Little, neat vanishings, rings, they realized. Not the kind you announce with trumpets dark, narrow, easily missed, yet they're all the same. A softer echo reaches further back. On the 22nd of February 1789, William Herschel wrote that a ring was suspected, even drew a delicate loop with a faint reddish cast. For 2 centuries, most doubted the claim. How could he have seen something so dark? The rings swallow almost all the light that finds them. Geometric albedo, no higher than to 5–6%. Bond albedo, near to 2%. Black on black in the cold. And yet, with modern eyes, the NIU new ring truly does show a reddish hue, an afterglow that feels like an old note answered at last. From that 1977 occultation, 9 rings were first tallied and labeled by the order of their blinks: 6, 5, 4, alpha, alpha, beta, et, gamma, gamma, delta, delta, and epsilon, an additional ghostly inner band. 1986 U2R, often nicknamed Zeta, the Zeta ring, would soon be added. Voyager 2, during its 1986 flyby, found 2 more faint rings. Between 2003 and 2005, Hubble saw a farther pair, Nu, and Mu, doubling the known radius of the system and fixing the total at 13. In September 2023, the James Webb Space Telescope turned its near-infrared eye toward the planet and returned one of the cleanest portraits yet, pale blue-green globe. Delicate loops, gleaming like threads of ice-black silk. Arranged from the planet outward, the rings run as follows: 1986 U2R Zeta, then 6, 5, 4, alpha, beta, ida, gamma, delta, lambda, lambda, epsilon, NIU, and mu SM. The closest sits roughly 38,000 kilometers from the planet's center. The farthest reaches near 98,000. Between them lie tenuous ringlets and veils of dust that appear and fade like breath on glass. During a rare ring plane crossing in 2007, when Earth looked exactly edge-on, some of those faint bands sharpened into view. Voyager had caught others via forward scattering, with sunlight skimming at a shallow angle to make tiny grains briefly outspoken. Composition sets the mood. These are not bright water ice mirrors like Saturn's. Their particles are ice mixed with radiation-darkened organics material, cooked by the planet's harsh environment, so they drink in most of the light that touches them. Many lanes are nearly dust-free, built instead from lumps and fragments ranging from about 20 centimeters to 20 meters across. A few bands, 1986 U2R, Eta, Delta, Lambda, NIU Mu, carry more dust, but even there, the finest grains don't linger. The planet's thin outer atmosphere, its exosphere, drags on motes and wisps, sweeping them away, while larger bodies, less affected by that faint break, remain. All signs suggest the rings are relatively young by solar system standards, no older than a few 100 million years, perhaps to 600 million. The likeliest origin is a violent, local story. Small inner moons nudged by resonances, struck by wandering stones or comets, shattered and ground down. The debris sifted into narrow corridors of gravitational calm and stayed. How those razor-thin lanes keep their edges so crisp is part gravity, part choreography. In one case, the answer is explicit. Epsilon, the brightest ring, is shepherded by two tiny moons, Cordelia inside, Ophelia outside. Their pull corrals the particles, keeping them from diffusing into a blur. Elsewhere, the faint Niu ring is hemmed by Portia and Rosalind, quieter hands performing the same steady work. For other rings, no obvious shepherds have yet been found, leaving resonances and collective self-gravity as the likely invisible scribes that draw sharp borders. Each ring has a temperament. Some are genuinely opaque, though only a few kilometers wide. Others 1,986 U, 2R, and NIU among them are gossamer, more dust than stone. Brightness ripples along their arcs, a slow shimmer as particles clump and thin, as shadows align and part. They also play a favorite optical trick, a steep opposition surge. When the sun sits directly behind the observer, tiny shadows vanish and the rings flare brighter, tip away even a little, and the glow falls sharply. Their color is peculiar, slightly red in ultraviolet and visible light, turning gray in the near-infrared, and their spectra show no crisp chemical fingerprints, as if the long reign of radiation has blurred every signature into the same dull ink. Among all the bands, Epsilon is the showpiece, densest, brightest, and most disciplined, reflecting roughly 2/3 of all the light from the ring system. And still, when viewed exactly edge-on, it can vanish as it did in 2007, thinner than a breath. ALMA has measured its temperature at about 77.3 K, 196 degrees Celsius. So cold, the idea of heat feels hypothetical. During Voyager's pass, radio instruments caught an elegant sign of order, a strong increase in forward scattering at a 3.6 centimeter wavelength, especially near the ring's farthest point from the planet. That pattern implies fine internal structure, a comb of narrower ringlets, and perhaps incomplete arcs nested within the main lane, all aligned just so. Epsilon isn't a perfect circle. It's slightly eccentric and almost perfectly flat. Near apoapsis, when the ring swings farthest from Uranus, it widens and brightens. Near periapsis, it narrows and dims. The change can be as large as a factor of 2.53. At its narrowest, Epsilon is on the order of 19.7 kilometers wide. At its broadest, roughly 96.4. Broader means less self-shadowing, more light bounced back, so width and brightness rise together. Its optical depth, how much it blocks and scatters light, ranges from 0.5 up to 2.5, greatest near the planet. The equivalent depth sits near to 47 kilometers and remains essentially constant around the ring, a tidy measure of how much material the line of sight crosses. The vertical thickness hasn't been pinned exactly, but models put it at a wisp, perhaps to 150 meters. Within that wafer, multiple layers of particles interleave, a tight, dynamic weave. Near the widest spans, the space is busy. The filling factor, the fraction of space actually filled by solids, has been estimated between about 0.06 and to 0.8, depending on scale, with average particle sizes in the tens of centimeters up to tens of meters and mean spacings of a few radii. Dust is almost absent, likely because the exosphere scrubs small grains out of the ring. leaving the larger fragments to obey the ring's law. Edges are kept by ratios that feel like music. The inner margin of Epsilon sits near a 24 to 25 resonance with Cordelia, the outer margin near 14-13 with Ophelia. Those small tugs, repeated orbit after orbit, balance the spreading that collisions and self-gravity would otherwise cause. For this shepherding to win the long game, the moons must outweigh the ring's contents by several fold. The ring's total mass is estimated around 10-16 kilograms, a light bracelet for a planet, a mountain's worth for us. Beyond Epsilon, the outer Nu and Mu rings feel like exiles faint, far, dusty, recalling Saturn's G and E rings in character. Closer in, the narrow, dark lanes invite comparison to Saturn's F ring, thin, eccentric, kept in line by shepherds. Jupiter's ring is a ghostlier veil, mostly dust. Neptune's are darker and arc-broken. Uranus's system sits between all of them, not as wide and icy as Saturn's, not as insubstantial as Jupiter's, not as simple as Neptune's. If each ring system is a dialect, Uranus's is written in a tight, lowercase hand. Their brightness is never uniform around the circle. Telescopes on Earth and instruments in flight see patches that gleam and patches that subdue, likely born from subtle shifts in particle size, local clumping, and gentle resonances. Dust bands that seem to appear and vanish have a habit of showing up in special geometries, forward scattering views, ring plane crossings, and then they retreat when the angles move on. Delicate is the right word, but fragile is not. This is a living balance that sways with viewing and keeps its shape. Underneath the grace is a familiar recipe: breakage and gathering. Imagine a set of small moons in close lanes, nudged by harmonies, sandblasted by micrometeoroids, struck now and then by a wayward comet. One fractures, then another. Shards grind each other smooth, and fragments sift into the corridors where gravity is most content. There, in ribbons only kilometers wide, they keep colliding quietly, darkening under the planet's charged rain. From certain distances, the rings look designed. Up close, the design is the sum of a trillion negotiations, each particle obeying the same simple rule. A few anchors to hold while the rest drifts. 13 rings, the first confirmed in 1977 by stellar occultation, a 19th century suspicion from Herschel that unexpectedly matches the reddish NIU ring. Inner lanes that are dense and dust-poor, outer ones that are faint and dusty. Geometric albedo under to 6%, bond albedo near to 2%, a steep opposition surge that turns darkness briefly bright when the sun, ring, and observer line up just so. Names that read like a small poem when spoken in order: Zeta, 6, 5, 4, Alpha, Beta, Eta, Gamma, Delta, Lambda, Epsilon, Nu, Mu. Even at their dimmest, patience is rewarded. In Webb's 2023 portrait, the rings look like wire loops set around a jade coin, each one a path of stones kept in line by math and chance. Cordelia and Ophelia are too modest to catch a casual glance, but their touch is written into Epsilon's sharp borders. Portia and Rosalind perform similar, quieter work near NIU. Elsewhere, invisible resonances and the ring's own collective gravity draw edges as clean as a knife. Everything is tilted: planet, rings, seasons. Everything is cold, and everything moves with a steadiness that feels like breathing. What's most astonishing is not only that such dark material can be seen at all, but that it can be kept so precisely arranged. A ring is a parliament of countless particles, each voting with its orbit, all settling into a common law. Here, the law converges toward narrow, flat, resilient. The magnetosphere paints and repaints the grains. The exosphere scrubs the dust. Shepherds keep watch. Resonances whisper. The outcome is a system unlike any other in the solar system, and yet kin to them all, recognizably a ring, yet speaking in Uranus's quiet accent. Stand with the few numbers a moment longer, then let them loosen. The closest ring near to 38,000 kilometers from the center, the farthest near to 98,000. Epsilon's width swelling from to 19.7 to 96.4 kilometers around its path. Optical depth from to 0.5 up to 2.5. Equivalent depth near to 47 kilometers. A possible vertical thickness of to 150 meters. Particle sizes from to 20 centimeters to 20 meters. A temperature near 77.3 K. A mass on the order of 16 kilograms. None of it interrupts the feeling. It steadies it. A thin parliament of stones and dust circles that tilted world, each lane holding to its place as if by memory. Gravity keeps the council together. Tiny moons do the guiding, their hands so light you can barely feel the touch. Some rings look nearly perfect from afar, and then, up close in the mind's eye, reveal moods brightening, thinning, swelling a little, and then settling like a tide that knows more rhythms than one. The Delta ring is like that, almost a circle, but set with the faintest lean from the planet's equator. Its light and thickness change as you walk around it in thought, bright here, subdued there, as if something small were passing on the inside and sending ripples through the crowd. Some astronomers whisper about a moonlet just within the ring, a pebble with enough pull to write waves. The sharp outer edge listens to Cordelia in a 23-22 rhythm, 23 laps for the ring particles for every 22 of the moon, a little metronome that keeps the boundary tidy. Delta is not one thing, but two in the same place. The first is a narrow, dense core, only about 4-6 kilometers wide, with an equivalent depth a little over 2 kilometers, and a normal optical depth near 0.3-0.6, surprisingly opaque for such a slim thread. Inside, that sits a broader, gentler component, to 10-12 kilometers wide, almost transparent, with an optical depth around 3 × 10 to the power of -2. Voyager 2 did not see this division as a picture. It heard it as a dimming in starlight during occultations, the way you can know a leaf is passing a porch light by how the glow falters. Later, when the spacecraft looked with the sun behind the ring, forward scattered light streaming through the broader section flashed bright, a giveaway that fine dust is mixed into that airy lane. In the edge-on view of 2007, Delta kept shining instead of vanishing, another hint that the wide part is geometrically thick but lightly filled, a gossamer layer more than a wall. The Gamma ring keeps a tighter line, narrow, dense, a little oval. It lies nearly level with the planet's equator, only to 3.5 kilometers wide, but it carries a steady equivalent, depth of 33 kilometers. Looked at from above, its normal optical depth sits high to 0.7, 0.9, an opaque ribbon in a dark sky. And yet, in 2007, when the ring plane aligned with Earth, Gamma disappeared completely. That vanishing act says, paper thin and dust poor, much like the brilliant Epsilon ring. When there's no thickness to catch the light, there's nothing to see edge on. Still, the ring's width and brightness change along its path, a small breathing. Its inner edge sits in a 6-to-5 resonance with Ophelia, an intimate tug that likely helps hold the border straight. The Eta ring lies nearly flat, almost a perfect circle, and like Delta, has two voices. One is a narrow central band, only to 2 kilometers wide, with an equivalent depth around 0.4 kilometers, and a normal optical depth to 0.16, 0.25. The other is a broader, faint skirt, stretching 40 kilometers outward, with an optical depth near 2 times 10 to the power of -2. Voyager 2 caught Eta clearly in images and saw it blaze in forward scattered light, a sure sign of very fine dust, especially in that broad outer portion. During the 2007 crossing, Eta became the second brightest feature of all, another signal that it is geometrically thick but only lightly filled. Around its circuit, brightness and width wander, and in places the narrow core even seems to melt away. Eta also dances with Cressida, near a 3-to-2 Lindblad resonance. 3 soft bulges and 3 dips ride the ring's circumference, drifting at the moon's pace, a slow, graceful wave that wraps the planet. After Epsilon's bold spark, the Alpha and Beta rings are the next most luminous, and they too wax and narrow with place. Brightest and broadest about 30 degrees from apoapsis, dimmest and most slender about 30 degrees from periapsis, eccentric orbits making light behave like a tide. Both rings carry small tilts and true eccentricity. Alpha swings between to 5 and 10 kilometers in width, Beta from to 6 to 11 kilometers. Their masses are each on the order of 5 times 10 to the power of 15 kilograms, about half of Epsilon's content. The equivalent depth for Alpha sits near to 3.25 kilometers, with a normal optical depth to 0.3, 0.7. Beta's equivalent depth is about to 2.1 kilometers, with optical depth 0.2, 0.35. During the 2007 edge-on view, they vanished, dustless and thin like Epsilon. Just beyond Beta, a faint, wide, dusty band showed itself, something Voyager had glimpsed decades earlier, reminding us that even in a strict system, there are veils between the rails. Closer in, the inner trio Ring 6, Ring 5, and Ring 4 are the narrowest and faintest of the lot, and more inclined and elongated than most, aside from Epsilon. Their small inclinations to 0.06 degrees, 0.05 degrees, 0.03 degrees were enough that Voyager 2 saw them riding to 2446 kilometers above the planet's equatorial plane. Strings just off the board. Ring 6 is only to 112 kilometers wide. Ring 5 spans to 25 kilometers. Ring 4 to 212.4. Their equivalent depths come in around to 0.4, to 0.9, and to 0.7 kilometers, translating to normal optical depths to 0.16, 0.48. In 2007, they were lost entirely to the eye, too dust poor and too thin to catch the shallow light. Together, these lanes sketch a quiet complexity. What looks like a handful of faint bands is, at heart, a balance of gravity, time, and touch, resonances with small moons, ripples from unseen moonlets, and the way dust brightens or vanishes depending on how the sun is placed. The system is a dance, and you can hear the music if you sit still for it. The lambda ring is one of the softest notes, first heard by Voyager, 2 inches 1,986, It hugs the inside of Epsilon, tucked between that bright band and Cordelia. Cordelia keeps the immediate inside lane swept clean, a dark trench that helps Lambda hold its shape. In backscattered light, sunlight, reflecting from the ring toward you, Lambda is a hairline, only to 2 kilometers wide, with a small equivalent depth to 0.2 kilometers at 2.2 micrometers. Unusual among Uranus's rings, Lambda's optical depth changes with color. In the ultraviolet, it can reach to 0.36 kilometers in equivalent depth. That is why Voyager first caught it in UV occultations, not in the visible. Only years later, in 1996, did astronomers confirm it at 2.2 micrometers, and the feature moved from rumor to roster. Change the geometry, and Lambda becomes a torch. In forward scattered light, it outshone even Epsilon during Voyager's pass. Dust doing what dust does best, scattering light with gusto when the sun is behind. The normal optical depth of that dust is tiny, to 10 to the power of -4, 10 to the power of -3, almost transparent, and still it blazes at the right angle. KEK's 2007 Edge-On observations showed the same thing. Lambda climbed among the brightest, a proof in living light that fine grains rule its mix. Its brightness also varies along the ring in a repeating pattern, like a standing wave wrapped around the planet. The cause is still an open door, another gentle mystery in a system that likes them. That same encounter revealed a ghost closer in, a broad, fragile sheet within the innermost lanes. Voyager's team tucked it under a temporary name, 1986 U2R, and filed it as barely seen optical depth to 10 to the power of -3 or less. For a while it seemed it might have appeared in only a single frame. Then, in 2022, a careful rereading of the old data found it in several post-encounter images, between 37,000 and 39,500 kilometers from Uranus's center only, 12,000 kilometers above the cloud tops. In the early 2000s, KEK watched a broad, faint band just inside Ring 6, and the feature got a new, older-sounding name, the Zeta-Zeta ring. Zeta did not stay put. By 2003, 2004, it stretched from 37,850 to 41,350 kilometers, with a faint inward taper reaching as close as 32,600 kilometers, possibly even down toward 27,000 kilometers above the clouds. Extensions labeled ZAC and ZAC in some notes, like tributaries traced on a map. In the 2007 ring plane crossing, Zeta became the single brightest feature in the entire system, forward and backscattered sunlight, turning nearly invisible dust into a beacon. Equivalent optical depth for the main band sat near to 1 kilometer, and about to 1.5 kilometers for the inward extension. The normal optical depth, though, was still minute to 10 to the power of -2 to 10 to the power of -3. Zeta rose above the equatorial plane by 800-900 kilometers, a true sheet rather than a thread. Part of the difference between Voyager's sighting and later views is angle. Side-scattered light then, back-scattered light later. Part is evolution. Dust is made and unmade all the time by collisions, radiation, and the faint winds of charged particles. Between the named rings, there are other, nearly invisible lanes, faint dust bands that barely register in occultations but flare in forward light. Voyager's shallow-angle images first drew them out, luminous streaks between lambda and delta, between eta and beta, and between alpha and ring 4. KEK found them again in 2003, 2004, and then once more in the 2007 geometry, though never quite in the same brightness or position as before. The numbers are wisps, normal optical depths only a few times 10 to the power of -3, vertical thicknesses around to 300 kilometers. Their grains follow a simple rule seen often in nature, a power law size distribution with index near to 2, 5 give or take to 0.5, which means there are many more tiny motes than larger bits, just as beach sand holds more fine grit than pebbles. Beyond even the visible rings and these secret bands, the whole system seems wrapped in a diffuse veil, an ethereal dust sheet extending inward from lambda toward the planet, so faint that its normal optical depth stays below 10 to the power of -3. Its vertical thickness is on the order of to 140 kilometers. It is almost nothing, and still it is there for instruments that are patient and attentive. All of this, the threads, the sheets, the waviness, the disappearances and sudden flares, adds up to a living, evolving set of bracelets. Voyager 2's 1,986 revelations were the first careful portraits. KEK's sensitive eyes in the 2000s, the 2007 ring plane crossing, and then Webb's near-infrared gaze have layered on depth. The system changes because it must. Dust is made by micrometeoroid strikes and ground from collisions, then removed by radiation pressure and aerodynamic drag from the exosphere. Resonances pull and release. Moonlets stir ripples that run for a while and then dissolve. And then there are the far-out lanes that Hubble brought into the family between 2003 and 2005, the wide, ghostly Mu, and Niu rings. They live far beyond the bright inner set, the Mu ring roughly twice as far from Uranus as Eta. Unlike the narrow, knife-edged inner rings, these are broad and almost not there. Mu spans to 17,000 kilometers, Niu about to 3,800 kilometers. Their light is so faint that it plots as a triangular rise and fall rather than a flat plateau, edges soft, centers subtle, along Mu's path. The brightest spot sits on the track of a tiny moon named Mab. It is an old story told new. Micrometeoroids pepper a small moon, send dust off its skin, and that dust, bound to the moon's orbit, spreads into a ring. Saturn's E ring owes much to Enceladus, Jupiter's main ring to Métis and Adrastea. Here, the Mu ring listens to Mab. The Niu ring, even dimmer, keeps its own counsel and likely has a similar source, a quieter stream from another small body. To sit with all these pieces is to let go of the idea that rings are simple. They are not frozen decorative bands. They are weather and water and shorelines in slow time, always remade. Delta's two-part body, Gamma's razor-thin opacity, Eta's twin voices and trotting wave with Cressida, Alpha and Beta's breathing widths, the innermost trio's narrow tilts, Lambda's dust-lit flare and standing wave brightness, Zeta's migrating sheet that blazes at the right sun angle, the diffuse veil that holds the whole interior in a soft net, and the far Mu and Niu rings with their moon-fed dust. All of it is one organism, breathing. If you keep only a few beads for comfort, let them be these: Delta's 23-22 conversation with Cordelia, Gamma's 6-5 tie to Ophelia, Eta's 3-2 wave with Cressida, Alpha and Beta, peaking 30 degrees from apoapsis and paling 30 degrees from periapsis. Rings 6, 5, and 4 so thin they vanish edge-on. Lambda, a 1-2 kilometers, line that outshines epsilon when the sun is behind. Zeta rising to 800 to 900 kilometers, brightest of all in 2007. Its normal optical depth only 10 to the power of -2, 10 to the power of -3. Dust bands with optical depths of a few times 10 to the power of -3 and to 300 kilometers tall. Mu and NIU wide and ghostly, with Mu's crest on Mab's path. Everything else can be allowed to blur into feeling. And the feeling is this: wreckage kept in order by kindnesses of gravity, lanes edged by ratios that repeat like lullabies, darkness made visible by the right light. Around a planet that sleeps on its side, the rings keep their quiet rounds, not static, but steadfast, changing just enough to remind us that time moves even in the cold. Far out, where sunlight thins to a silver thread, 2 ghost rings keep station: the wide, whispery Mu, Mu, and the even fainter Nu, Nu. They are nothing like the knife-edged lanes nearer in. Mu is a pale sash, some 17,000 kilometers across. Mu is narrower, a few thousand, lying between the tracks of Portia and Rosalind, with no known moon inside to herd it. When old Voyager 2 frames were reread in the soft geometry of forward scattered light, both rings bloomed from near invisibility. That glow gave away their secret. Clouds of micrometer dust, lighting up only when the sun sits behind, the way breath shows only in winter air. The pattern felt familiar, like Saturn's delicate outer rings G and E, where faint dust rules the scene. Saturn's E ring feeds on snow blown from Enceladus. Mu likely sips from little Mab, its dust tapped loose by tiny impacts and carried along the moon's path. Later, the KEK Observatory watched in the near infrared around 2.2 micrometers. It saw Nu and not Mu, a quiet clue. Mu must reflect more blue light, very fine, sub-micrometer grains of ice, or ice laced with faint darks. Mu trends slightly redder, a hint of larger motes, or more seasoned, less icy skin. In that color lies a story about size and age, and how radiation paints surfaces over time. What keeps rings this narrow, this precise, from unspooling? Left alone, the lanes would spread and blur in less than 1,000,000 years. The favored answer is pastoral, shepherd moons. Put a small moon inside and another outside, and their opposing tugs confine the traffic between them. It's a slow trade. While they steady the ring, the shepherds themselves drift, their orbits shifting grain by grain. For the trick to work, each moon must outweigh its ring by a factor of a few. We've seen the principle in the brightest band. Epsilon, Cordelia inside, Ophelia outside. Cordelia doubles as the outer keeper for Delta, while Ophelia tends Gamma. Elsewhere, no guardian larger than about 10 kilometers has been found. If they exist, they are small, secretive, or both. By reading the current positions of Cordelia and Ophelia, astronomers have even sketched Epsilon's age, not more than roughly 600 million years, young enough that renewal must be ongoing. Renewal is simply the universe's way. Collisions break, collisions build. Over billions of years, small moons and big rocks meet, fragments collide, again and again, collisional cascades grinding down from boulders to gravel to dust. Most of it is lost to the planet or blown away. Some falls into resonant lanes and stays. A moon the size of Puck could live for a few billion years before fate and chance make an end. Smaller ones would fail sooner. The narrow rings we see now may be the late song of many vanished moonlets, their debris sifted into seams, then trimmed by shepherds and subtle harmonies. Dust, at least, is easy to understand and quick to leave. Its lifetime is short, hundreds to 1,000 years swept by radiation pressure, sputtered by charged particles, slowed by whisper-thin air at the edge of the planet's exosphere. So the glow we catch in forward light must always be new. Fresh dust shakes loose when meter-scale chunks bump, when micrometeoroids pepper a surface, when a faint moon is struck and sheds frost. The big lanes of main rings, rich in decimeter to meter-size fragments, shine and backscatter. The dust bands, poor in large pieces, fade in that geometry and flare only when the sun stands behind. Webb's near-infrared eye added a soft layer of truth. Between 1 and 5 micrometers, epsilon remains the brightest of all. At the shorter end, you can tease apart rings 4, 5, 6, along with alpha, beta, eta, gamma, delta. Push to longer wavelengths, and their separate voices blend, as if distance and particle size smooth the choir. Spectra show that, around 3 micrometers, the rings absorb less water-ice light than the inner small moons do. Perhaps the ring particles carry less surface frost. Perhaps they are larger and thus less reflective. Farther from the planet, the water-ice signature strengthens. The outer rings may keep more ice intact. Mab and Puck wear unusual colors in this light, hints that icy grains are exchanged between rings and moons, a winter of drifting snows passing back and forth. When Voyager 2 came calling in January 1986, it did more than count. It listened. Radio waves, ultraviolet, visible light all sent through the rings during occultations, all dimmed and delayed in ways that mapped thickness, density, and texture. The spacecraft circled the planet's shadow and caught the rings in backscatter, forward scatter, side scatter, drawing full-phase curves that told how particles reflect. From those curves came brightness measures, geometric and bond albedos, and a feel for composition and size. In the images, epsilon and eta were crisp enough to show fine substructure, narrow ringlets, clumps, scallops, little signatures of hidden physics. And in the playing out of its pictures, Voyager found 11 inner moons. 2 of them, Cordelia and Ophelia, were the shepherds that theory had promised, small guardians keeping epsilon from smearing into dark. The view turns gentle and red farther in the night. Orion's belt leans above the horizon, and below the easternmost star, Alnitak, a small darkness lifts its profile from a velvet glow. The Horsehead, a pillar of dust silhouetted against IC 434's hydrogen light, part of the Orion molecular cloud, close enough, about 1,375 light-years, that we can trace filaments like hair caught in wind. Williamina Fleming first noted it on a Harvard plate in 1888, a brief mark on glass that would grow into one of the sky's most beloved shapes. Edward Emerson Barnard later tucked it into his catalog as Barnard 33. It is the simplest of illusions, a backlit fog. The red is hydrogen alpha, lit to incandescence by nearby hot stars Sigma Orionis. Among them, while the horse-shaped trunk is merely dust so thick it drinks the light behind and throws a shadow across our line of sight. The border where bright meets dark is sharp, a rim along IC 434, where ionized gas ends and cold cloud begins. On one side, glow and density waves and plenty of visible stars. On the other, lanes where starlight thins to almost nothing. Magnetic fields thread the region, guiding gas into long, fine streams that look like handwriting when seen in deep exposures. Inside, the dark is not emptiness, but work. Protostars gather in knots, where gravity wins the quiet tug-of-war against pressure and turbulence. Some of the small points near the base are infants, still wrapped in their swaddling dust, not yet hot enough to fuse, only bright enough in infrared to give themselves away. The cloud is rich in molecules, carbon, oxygen, nitrogen compounds, material that absorbs the visible and glows softly in the mid-infrared, a wavelength where Hubble and Webb can see through the soot. In those bands, the Horsehead's interior shows filaments and curls, eddies and beads where new suns will soon be named. This little figure is part of a larger family, the Flame Nebula nearby, NGC 2023's reflection glow, the Great Orion Nebula, M42 down the Sword, one complex of birth, fed by the same reservoirs of cold gas. That is why Orion pulls at us in winter. It is not only a familiar pattern, it is a working story. You can step out under the sky, see 3 stars in a row, and know that behind them is a whole engine of making and unmaking. The Horsehead looks still in photographs, but it is not. Radiation gnaws at it. Stellar winds comb and thin its mane. Over long spans, the trunk will unravel, the edges will soften, and the outline that has taught so many eyes to love the sky will fade. What will remain is what always remains, the stars it helped raise. In that sense, it is like Uranus's rings, a shape made by balance and circumstance, beautiful because it will not last, precise because so many small forces agree for a while. If you want a few beads to hold, you can keep these and let the rest stay music. Mu and Niu, broad and faint. Mu, blue bright, with sub-micron ice from Mob. Niu a little redder and dustier. Forward scatter as the trick that reveals what would otherwise be nothing. Shepherds as keepers of narrowness. Epsilon, hemmed by Cordelia and Ophelia. Delta, listening to Cordelia's 23-22. Gamma, tuned to Ophelia's 6-5. Eta, breathing with Cressida in a 3-2 wave. Dust made and remade in centuries, main rings bright and backscatter because their stones are larger. Bands bright in forward light because their dust is fine. Webb's spectra, epsilon brightest in 1.5 micrometers. Outer rings carrying stronger water ice signals, small moons and rings trading frost. Voyager's occultations mapping thickness and grain. Its camera finding shepherds where theory said they should be. And then the Horsehead. Barnard, 33, against IC 434, 1,375 light-years away. Edges sharp where ionized gas meets cold dust. Magnetic fields teasing gas into filaments. Protostars tucked at the base. Molecules humming in infrared. Part of a larger nursery that includes the Flame and the Great Orion Nebula. A figure that will erode and yet has already given its gift. None of this asks to be solved tonight. It invites you to breathe with it. Rings held taut by the lightest hands. Dust lit only when the sun and time align. A cloud that looks like an animal because we love to name. New stars being folded from old material. The universe does not rush. It holds a shape just long enough for us to see it, and then, kindly, it changes into the next. Set your shoulders down. We'll drift a little closer to a bright coin set on edge in the dark. Astronomers call it the sombrero, M104, NGC 4594, tilted just so that a luminous bulge rises from a razor of shadow. It lives where Virgo leans toward Corvus, about 29-32 million light-years away. Through small glass, it's a neat glow with a piercing center. With more reach, you see the wide brim, a dark, perfectly poised dust lane wrapped around its disk. What puzzled first eyes and still charms the patient was how it wears two faces at once, a spiral's disciplined ring of dust and gas, an elliptical's swelling, star-rich heart. A hybrid, not by compromise but by confidence, hanging at the southern edge of the Virgo supercluster's long, thready outskirts. Numbers serve like soft fence posts here. Its diameter runs near 95,105,000 light-years, akin to our Milky Way's reach. Its blue absolute magnitude sits around 21.8 to 21.9, bright enough to be the starriest neighbor within roughly 33 million light-years. The halo, once thought modest, proved vast in Spitzer's sight, an enormous, massive envelope that tipped the scales toward more than a spiral, while that crisp, cold ring insisted, gently, not merely an elliptical. In between those claims, the galaxy makes its own category. The dust lane is no smudge. It is a ring, symmetric, exact, containing most of the cold atomic hydrogen and fine dust, with likely reservoirs of molecular gas. In infrared spectra, the truth softens into clarity. That ring is where new stars are actually forming quietly along the brim. The center says something different. It's a liner, weakly ionized gas lines in the nucleus, but not from a rush of newborns. Webb and other eyes find little sign of central starbirth. Instead, the mild ionization glows like a reflection off deeper power, an active black heart. In the 1,990 seconds, using Hubble and the Canada-France-Hawaii telescope, John Cormandy's team measured the whirl of stars near the core and found speeds that only a huge hidden mass could explain. The answer was an old story told anew. A supermassive black hole, about 1 billion suns. It is the closest billion solar mass black hole to Earth that we know, near enough to feel personal and far enough to remain perfectly safe. A lighthouse without a shore. Around it, electrons race through magnetic fields and whisper in radio and X-rays, synchrotron music, but not the wild kind that flares and dims by orders of magnitude. Sombrero's notes vary only gently, by 10 or 20%, as if the central engine prefers steadiness to drama. In 2006, a stranger chord appeared, emission near 850 micrometers, terahertz light that refused familiar boxes. Not dust warmed in the usual way, not standard synchrotron, not the thin breath of hot gas. The source remains unsorted, a small riddle tucked under that enormous hat. Look away from the nucleus to the old and crowded, globular clusters where our Milky Way keeps a few hundred. Sombrero tens perhaps 1,000, 200, 2,000 tiny ancient cities of stars. Count them against the galaxy's brightness, and the ratio runs high, much like galaxies with large, brilliant bulges. Map their density, and you see a pattern. They thin with radius as the bulge's light thins. Then the rule bends near the center. Their abundance feels less like trivia and more like a signature, tying the size of the bulge to how many globulars it shepherds. Distances here are measured with several gentle rulers, each one humming its own tune. Planetary nebula luminosity functions compare the light of small, glowing clouds there with kin in our own galaxy to 29 million light-years, give or take. Surface brightness fluctuations read the grain of unresolved stars in the bulge. Early tries gave to 30.6 million light-years. Refinements moved it toward to 29.6. Weave the measures, and you arrive around to 29.3 plus or minus 1.6 million. In 2016, Hubble tried a subtler needle, the tip of the red giant branch, that sharp shelf where old stars crest in brightness, and stitched a distance near 9.55 mpc with tight error bars. The numbers do not argue, they harmonize. Mass gathers under those lights, perhaps 800 billion suns all told. The galaxy sits inside a slender filament of galaxies that arcs from Virgo's crowded hub. Whether Sombrero belongs to a formal group depends on the method. In hierarchical pictures, it links to several companions: NGC 4487, 4550, 4804, UGCA 289, and others, while friends of friends, catalogs sometimes shrink the cast to a quiet pair with UGCA 287. Add to that one curious jewel, an ultra-compact dwarf found in 2009, absolute magnitude around 12.3, an effective radius of only to 48 light-years, yet a mass near 33 million suns. A box of stars dense enough to make your breath catch small, bright, improbable, and it lives in the Sombrero's shadow. If you'd like to bring it into your backyard, you can, from Speakawalk to 1112 degrees west, from Eta Corvi move to 5½ degrees northeast. In 7 times 35 binoculars, or a 10 cm telescope, a bright kernel with an elongated haze. In 20 centimeters glass, the bulge separates from the disk, with 25-30 centimeters. The dust lane is plainly drawn like an ink stroke between brim and crown. The night expands, and we glide from a galaxy's cool geometry to the warm, breathy work of 2 massive stars shaping dust. In Cygnus, between Deneb and fainter points, a star listed as WR 140, also V1000, 687, Sig beats time you cannot hear, and still every shell remembers it. It's a spectroscopic binary, the kind that hides its double self until spectra shift. One O-type giant, or supergiant blue hot and mighty, and one Wolf Rayet, a rare, stripped furnace near the end of its brief life. Their orbit is a long ellipse, about 7.9 years per turn, a close brush, then a long drifting apart. At Periastron, they are only to 1.3 AU apart, closer than Mars's path. At Apastron, nearly 24 AU wider than Uranus's lane. Where their winds collide, thousands of kilometers per second meeting head-on, shocks rise, temperatures leap, and carbon-rich material condenses into dust, not everywhere at once, but along a curved interface that wraps like a spiral and sheds like a skin. Near Periastron, dust production surges. The system brightens in infrared, then slowly fades for months as the newborn grains cool and drift. From Earth we saw hints, 1 or 2 shells in the late 1990 seconds and early 2000s with Keck. Then Webb turned its mid-infrared ear in July 2022, and the whisper became a choir. 17 distinct rings, arcs upon arcs, out 2 to 45 arc seconds, roughly 70,000 AU. The outermost rings mark more than a century of pulses, each an 8-year page, upturned. The dust is carbon-rich, hydrogen-poor, exactly the chemistry a Wolf-Rayet outflow promises. Spectra of a bright knot. Astronomers nicknamed it C1. Show features akin to polycyclic aromatic hydrocarbons, rugged carbon molecules that often ride interstellar dust. Watch the shells carefully, and you can see them accelerate. Radiation pressure from the stars pushes them faster as they expand. Near to 50 AU, fresh grains move at to 1,800 kilometers per second. Within a year, they gather another to 900 kilometers per second. Farther out, as the grains thin and cool, the push eases. Two windows tell one story. Mid-infrared sees cooler, larger grains to 500 K, 30-50 nanometers, and near-infrared catches tiny 1 nm sparks near to 1000 K. Those ultra-small bits likely form when larger grains are shattered by collisions or by radiative torques that twist and tear. Why so regular, so round? Many colliding wind binaries make dust, but few draw rings like compass circles. Some of the symmetry is orbital, an eccentric path, a periodic close pass, a fixed geometry where winds meet. Some may be interior pulses from deep nuclear cycles in the Wolf-Rayet core, a thermal rhythm that modulates how much carbon is cast into space at each periapsis. The 8-year spacing matches the orbit, but the steadiness hints that the star itself keeps good time. New shells were seen around 1985, 1993, 2001, 2009, each ring about 1.4 trillion kilometers from the last, if you translate time into distance. Imagine our sun doing the same. A shell set loose today would be past the Oort cloud before the next one left, almost 5% of the way to Alpha Centauri. Under the physics is the feeling, a giant sloughing skins of carbon, warmed by light, pushed by light, cooled by distance. Each shell, a safe house for molecules that will one day seed other places with the ingredients of dust, clouds, planets. Wolf-Rayet stars can reach fierce surface temperatures, tens to hundreds of thousands of Kelvin, and their ultraviolet glare would seem hostile to grains. And yet here, the geometry shelters the first tender crystals long enough to grow. The result is delicacy, writ large. We know how such a star comes to this late style. Hydrogen gone from the core, helium takes its turn, fusion moves outward into shells, pressure waxes and wanes. The outward wind rises and falls as the engine inside surges and rests. Some cycles push more mass, some less. In a binary, the companions wind and gravity mark the dust with their own steadying signature. Whether the near-perfect rings are mostly orbital or partly heart-deep, the pattern itself is solace, stellar time, made visible, kept faithfully for decades. Stand back from both scenes, the sombrero's brim and crown, WR-140's necklace of rings, and the kinship is clear in the quiet. A dust ring in a galaxy is where stars begin. A dust ring around a dying giant is where elements gather to go elsewhere. In both, darkness is not absence, it is material in the making. In both, light does the revealing, back scattered, forward scattered, side scattered, turned into radio, into X-ray, into the mid-infrared glow of warm grains. The instruments differ, the scales defy easy comparison, but the rhythm of cause and effect is the same. Gravity shapes, radiation writes, time gently edits. If you want a handful of anchors to keep the mind from drifting too far, M104, shining at to 2932 million light-years, hybrid in Sol, a 1 billion solar mass black hole at its center, a ring that births stars along the brim, an odd 850 μm note that refuses a simple label. 1,000, 200, 2,000 globular clusters cupped in a vast halo, mass near 8 times 10 to the power of 11 suns. And, in Cygnus, WR 140's 7.9-year orbit, periastron to 1.3 AU, apastron to 23.9 AU, 17 rings to 70,000 AU, grains at 500 K and to 1,000 K, accelerations of hundreds of kms, a carbon chemistry that prints PA-like features, shells formed around 1,985, 1,993, 2001, 2009, spacing to 1.4 times 10 to the power of 12 kilometers. The rest can remain soft. Somewhere, right now, in the Sombrero's dust lane, a small blue star is learning to burn. Somewhere else, in WR 140's newest ring, a carbon grain is cooling and coasting, waiting to join a cloud it will never see, to become a world. The night is made of these cross threads. You can close your eyes and still feel them. A hat of light worn at the edge of Virgo, a necklace of rings unfolding near Deneb. We'll breathe with them a moment longer, unhurried, warm, then let them drift, the way all careful stories do, into the dark that holds them. Out where our galaxy thins to a breath, Webb turned its golden face toward the outskirts, nearly 60,000 light-years from the crowded heart, where starlight tapers and the darkness loosens into intergalactic night. The airless hush out there is made of hydrogen's faint smear, motes of dust, and a few cold clouds that still remember how to make suns. In the inner Milky Way, birth is loud, gravity tangled, radiation fierce, metals plenty, but at the edge the recipe is simpler, thinner gas, fewer heavy elements, a quieter hand. It's a little like peeking backward in time, to an era when galaxies were just learning their craft. To listen well, Webb used both of its softest instruments, NIRCam, to gather the near-infrared glow that slips past dust, and MIRI to hold the warmer, longer hues. The target was a pair of remote molecular clouds, first sketched decades ago, now called Digel 1 and 2. Within them, 4 pockets, labeled 1A, 1B, 2 north, and 2 south, were chosen as windows. In older telescopes, those windows looked like smudges. In Webb's light, they opened. Cloud 2 south was the most talkative. At its center sat a small, bright knot of newborn stars, only a few million years old, still drawing in their swaddling gas and flinging it back out as jets from their poles. In infrared, those jets gleam like silver needles. Each pinprick marks a disk, a nursery flat as a coin that may one day host planets. Near the cluster's shoulder, a smaller subcluster came into focus at last, only suspected, before suggesting that star birth here moves in waves. One group lights, then nudges the next. Shock fronts, soft radiation, a tug on the nearby gas that says, "Your turn." Around the stars, the scene is carved and puffed by wind. Reddish veils fold into one another. Cavities open where the young push the medium away. Ridges glow where the light strikes a denser edge. Through the thinner curtains, the deep field rises. Far background galaxies, little spirals, soft ellipses, tiny red beads stretched by the universe's expansion pepper the canvas. They remind us that even in a study of our own outskirts, the rest of the cosmos keeps company. Old light, passing behind new birth. These details are not only beautiful, they are instructions. The colors tell temperature, the brightness and texture trace density. The jets whisper about magnetic fields and how quickly the infants are feeding. In places rich in heavy elements, stars tend to form quickly and in crowds. Out here, with fewer metals to cool the gas and fewer kicks to compress it, the process is slower, more deliberate, often in small groups. Webb's sensitivity finally lets us measure that rhythm instead of guessing it. From such measures, estimates of masses, of how long the clouds can keep building before winds break them apart, of how much gas remains for the next generation. Each exposure is a ledger line in the Milky Way's long accounting of its own growth. Light from these rims began its journey before any of our stories were written. What we see is not tonight's truth, but a postcard from tens of thousands of years ago. And yet the motions are familiar. Collapse, ignition, outflow, the sculpting of nebula by young suns. In watching, we are not only witnessing the edge of our galaxy, we are looking into the kind of room where our sun once learned to breathe. Far beyond even that, Webb caught the glimmer of a different chapter, a first light ember from the universe's childhood. Astronomers give it a long name that reads like coordinates. We can call it a dawn galaxy, seen when the cosmos was only about 300 million years old. Its light is shifted so far into the red that near-infrared cameras first found it by absence. It vanished at shorter wavelengths and appeared only in the long, a classic Lyman break signature of extreme distance. Spectra, then, set the scale with Care redshift, a little over 14, which translates to a look-back of roughly 1310 billion years. On Webb's mid-infrared stage, the note continued cleanly, strengthening the case that this was not a trick of dust or a nearby imposter, but a true beacon from cosmic dawn. It is small by modern standards, a body perhaps 1,600 light-years wide, but for its age it shines fiercely, packed with hot young stars and the glowing gas they ionize. Later, on Earth, ALMA turned its cold ears to the same patch and caught oxygen's faint line there, the farthest such detection yet. Oxygen is not a first-day element. It is minted in stars and flung out when they die. To find it so early is to learn that the universe was quick on the uptake. The first stars must have formed, lived hard, and ended in rapid succession, seeding the next generation with the materials for complexity. Even the mass estimate hundreds of millions of suns and stars already pushes our models to hurry. Before Webb, we expected bright early galaxies to be scarce. Now we count more than we thought, by about an order of magnitude, and we will need to retune our understanding of how swiftly structure rose. There is a lovely precision in the numbers, and a humility too. Independent measurements agree within a breath. Oxygen's line and carbon's whisper match the same distance. Uncertainties narrow until the object's place in time becomes certain. But the feeling of it is simpler. This is a flash from the first pages, proof that the universe did not dawdle. It made and it remade, and it taught light to find us. All along this journey, from a ringed planet's dust to the pillars where stars climb out of shadow, from a wheel-shaped galaxy sparked by collision to a hat brim of dust where stars form across a bulge, from a small, blue, compact dwarf that looks young because it waits long between heartbeats to a pair of giant stars, weaving carbon shells in a slow pulse. The lesson repeats. Order rises from motion. Delicacy is not fragility, it is poise. Light arrives late, but faithfully, carrying maps of places already changed. And Webb quiet, far from Earth at its cool ill. Too perch does not make the universe, it listens. It gathers heat so faint you could mistake it for silence, and turns it into pattern. Jets in a remote nursery, ringlets of dust around a dying giant, a dust lane that circles a billion solar mass night at the heart of a galaxy, a thread of oxygen in an ember from the first dawn. Each pattern is a story told in a different alphabet, and together they read as one long breath, in and out. If you need a few anchors to keep, pocket them lightly and let the rest soften. The outskirts of our galaxy, to 58,000 light-years from the center, where stars still form but slower, gentler. Cloud 2 south, a bright cluster, a smaller subcluster, jets like needles, waves of birth moving through thin gas, background galaxies shining through like old coins, pressed under paper. A dawn galaxy at redshift to 14. Its light left when the universe was to 2% its current age. Oxygen already present, meaning stars had lived and died quickly. Mass on the order of hundreds of millions of suns. More early bright galaxies than we guessed. Not facts to hold tight, just touchstones if your mind likes them. Everything else can be feeling. The way dust is both obstacle and instrument. The way gravity and light share the work. The way a telescope can be a time machine without ever moving, simply by keeping still long enough. The way our own beginning is mirrored in a far cloud's first fires. Now the room is quiet. The constellations have stepped back behind the roofline, and even the crickets are counting in slower numbers. Let your breath match the night, in and a long, easy out. Somewhere a new star is blowing its first jet into dark. Somewhere a very old ring of dust is cooling into a curve. Somewhere a tiny galaxy is writing its first sentence in oxygen. We can let them be. We'll leave the mirrors to their watch, the light to its long road, the stories to their patient unfolding. Close your eyes. The universe will keep breathing. We'll begin again when morning asks for it, unhurried, warm, and for now, we rest.